So my name is Greg Belgrad, and this video is about a public lecture presentation I recently attended here at Georgia Tech. So the presentation was given by Dr. John DePilly of the University of California at Riverside on April 2nd, 2014, and the lecture was titled Illustrated Special Relativity Through Its Paradoxes. And this whole lecture focused on the aspects of linear algebra, graphing, and the reality of physics and special relativity, and how we really um, how we interpret the world around us and how we interpret time and space. And this whole lecture is very interesting and really opened your eyes on the world around us. So Dr. DePolice starts the presentation with a train paradox. So now the prompt goes, when a train pulls into the station, which end is younger, the front or the end? Well, one might think the end would be younger relative to the viewer because it pulled into the train station last. But due to special relativity, the front would be younger, which is very counterintuitive because it pulled into the station first, meaning by your reference frame it should be older, but that's not always the case. In fact, that's never the case. It's very counterintuitive and it's really confusing at first, but the answer has to do with special relativity, and we'll talk about that later so you can understand how this could be possible. And at least this prompt was very interesting to me, because how could something that came in first be younger? It was very interesting to me, so I decided to look up more about it and how time passes and how we interpret time. So, special relativity. So there are two main axioms of special relativity. Number one, the laws of physics are equally valid for all frames of reference. So no matter where you are observing, whether you're on a passenger on a train or a person on a platform, the laws of physics are constant. So no matter where you are and what you're observing, the laws of physics are equal through all frames. And number two is the speed of light is the same for all observers, regardless of the motion of the source of the receiver. So the wave speed of light is independent of the speed of the source. So I like to think of this as a thought experiment Albert Einstein did. So let's say you're sitting in a car and you are moving at, let's say, 20 meters per second, and light is coming from the headlights. So one might think at the added velocity of the car would make the light travel faster. Well, that's actually not the case. The speed of light is constant no matter what. So it doesn't matter how fast the car is moving, the speed of light would always remain the same. For normal objects, if you would add velocity from the source, the velocity of the whole system would increase. But for light, it's a very special case because light is so fast, but also light is constant. The source doesn't matter. So wavelength or wave speed is fully independent from the speed of the source. So how does this relate to the train? If anything, the laws of physics are equally valid for all frames of reference would be more relatable to the train than the speed of light would. Well, as we continue, one would be able to see how you can relate the speed of light to the train and the age difference between the ends. So the properties of inertial frames. Number one, all frames are identical when at rest. So imagine a scenario where you have a passenger on a train and a passenger on the platform. So at time zero, when they're at rest, or when the velocity is zero, the frames are identical. So no matter where you look, whether it's the passenger on the train or the person on the platform, the two frames are identical. So there's no difference in the environments. Number two, observers within any frame are fixed. So in any frame, so if you're the main point in a frame, you are not moving. So if you're on the train and you're the observer on that train, you are not moving relative to the frame. But if you're the person on the platform, you are not moving relative to that frame. So number three, communication between frames can only occur through a perpendicular line of sight. So you need to essentially be looking directly at a point to see that reference frame or to communicate with that reference frame. So your line of sight needs to be directly pointed to it. So number four, all frames are synchronized at zero. So all frames are synchronized. They all have the same time. Time applies, well, not necessarily equally, but they're all synchronized. And I'll tell you what that means later. Time is not standardized between the frames, but they are synchronized, to say the least. So, number 5, relative speeds between frames are negative symmetric. So here's how you can interpret this. So let's say I'm a passenger on a train, and that train is moving forward. In my reference frame, I am not moving relative to the train, but I could be coming across a platform, and I could see a person on the platform, and as I pass by, that person is going to the rear end of the train. So relative to me, that person is moving with a negative velocity. However, if my reference frame is at the is with the perspective of the person on the platform, that person on the train is moving in a positive direction. So relative speeds between frames are negatively symmetric. So if you're looking at if you're taking the same situation with two reference frames, the speeds between the two frames would be negatively symmetric. So they are the inverses of each other. Well, not necessarily inverse, but they are the negatives of each other. So one of the paradoxes the presenter introduced was the twin paradox. So here's how it starts out. A set of twins starts out at newborn, so year 0. And one twin is chosen to remain stationary for a time, in this case it was 50 years, and the other twin travels at 0.8 times the speed of light for the same amount of years relative to the stationary twin. And as 50 years passes, the stationary twin is obviously 50 years old, but the moving twin is 30 years old. And this all kind of relates back to how our perception of time and space has changed over the course of many years. When Isaac Newton came up with his idea of the universe, he thought the only thing constant was time. But when Albert Einstein came along and realized that the only thing constant in the universe is energy, conservation of energy, he realized that depending on your reference frame, time can actually change. So time isn't constant. Depending on how fast you're traveling or where you are, time can actually change. Your perception of time can change. So Isaac Newton was wrong. Time is not constant. The way time moves is not constant. In fact, it is far from constant. So that's where this comes from. So when you're traveling, time actually slows down, is the main point to get from all this. As you travel closer and closer to the speed of light, time begins to slow down. So when you're stationary, time can move constantly. But as you speed up, time slows down. The second paradox the presenter introduced was the bug rivet paradox. So the problem statement starts out like this. A bug is placed on a rivet between two steel plates. So you have two reference frames, one where the rivet is moving and one where the plates are moving. So there would be two outcomes in this situation. The rivet shrinks because it's moving and the bug does not become squashed. Or the walls shrink in distance between the two and the bug is squashed by the rivet. So how does this work? One of the things with special relativity is that in the direction you move, the distance between the ends of objects decreases. So an object would shrink in the direction it moves. So depending on your reference frame, the rivet can be moving, and that could shrink. So the bug at the end of the rivet would drop down, but as soon as the rivet would come back out and can come back in, it would be shortened, so the bug would not become squashed. However, in a different reference frame, the plates could be moving, and the distance between those plates shrinks, and the rivet could become longer relative to the plates. and then the bug would become squashed because the distance of the plates has been decreased, and the distance the rivet has to go in is decreased, so the bug will get squashed as it falls, assuming the rivet's exiting and coming in fast enough. So, in summary, the perception of time and space when moving has two aspects associated with it. Number one, moving clocks slow down and interpret time more slowly as an object moves, but also as an object moves, it shrinks in the direction in which it's moving. So, one of the concepts I looked at outside of lecture was the concept of time dilation. So, as stated previously, as one approaches the speed of light, time slows down, and the faster one goes, time passes increasingly slower, meaning the faster one goes, time passes more slowly. So it's almost a function of time. Your perception of time is a function of how fast you are moving. So, and this is really interesting, when one approaches the speed of light, assuming one can even reach the speed of light, time stands still. And this can be explained with the next graphic in the equation, this generalized equation. So time dilation, which is the perception of time, which is denoted t apostrophe, so t prime, is equal to time in general, like the actual time, divided by the square root of 1 minus the quantity, the velocity of the object squared, divided by the speed of light squared. So as one could take the limit as v approaches c, and as this velocity eventually becomes equal to the speed of light, that whole quantity becomes 1, and then that whole quantity in the denominator becomes 0 over time, so that as the velocity goes to the speed of light, time dilation would eventually become infinity. So what that essentially means is as you approach the speed of light, time stands still. So if you look on the y-axis, the time dilation axis, that's just how much slower you interpret time. So as you approach the speed of light, you're approaching a time dilation of infinity, which means you would interpret time infinitely slow, meaning time would just eventually stand still. Now obviously one can't, with current physics models now, one can't exactly get even close to the speed of light, let alone to the speed of light itself. But that's the whole thing about time dilation. So this is kind of merely an expansion of what the presenter talked about in lecture, because he never really went over the concept of time dilation itself. He just kind of stated that as you move, time slows down. He didn't necessarily say how or why it slowed down. So this is just kind of looking at time dilation outside the lecture and kind of delving more into how time slows down based on the velocity of an object. So this is kind of what I took away from it and how time slows down. So this is kind of what I did outside of lecture, and how you interpret time as you move really interested me. So as you obviously increase in velocity, you're on your way to effectively making your perception of time stop. So that's very powerful, and I'm not saying we will get there at any point, but at least theoretically it could be possible. As long as you can get to the speed of light, time will stand still. So in conclusion, I thought this lecture was very interesting. Special relativity is a very interesting topic, and time dilation is certainly a very interesting topic as well. That's why I decided to research more about it outside of lecture. And I really feel like this whole lecture has really helped me understand the world around me in a bit more detail. It certainly does make you a little confused at first, because a lot of the ideas are counterintuitive and confusing. But I feel like special relativity makes you understand the universe and the surroundings as a whole a lot better, because you can't think of everything so linearly, which was the mistake Isaac Newton made, especially when it comes to interpreting time, because he thought time moved in a linear fashion, when in reality, at least time dilation proves it does not. So I feel like special relativity helps you think outside the box in terms of interpreting the world around you. And that's why I think this lecture was very valuable, and that's why I think this lecture was just very, very interesting. So I hope you appreciated my follow-up video to this, and I hope you research special relativity and time dilation a lot more. So thank you so much for watching, and this has been a very pleasurable and interesting experience.